A ver, por favor, Perdón. Okay. So, hello, everyone. Today, it's my turn. I'm going to talk to you about digital analog quantum computation, which is the field that I am working on during my PhD thesis. And hopefully, depending on how fast I speak, I would like to tell you more about the famous HHL algorithm that I have been working for the last too many years to say it out loud. Okay, so let's start by the digital quantum computation paradigm. I assume that all of you here knows what is this about. It is the most extended quantum computational paradigm, and the building blocks are single qubit gates to change the state of a single qubit. These are simple digital pulses. And two-qubit gate to create both entanglement and superposition among the qubits and the system itself. And this is done by applying digital pulses simultaneously to two qubits. This has been shown to present high fidelity rates in the implementation of short-depth quantum algorithms using these NISQ devices, which are the noisy, small devices that we already know. The drawbacks of this paradigm is as the depth of the algorithm increases, the resources we need to implement it increase as well, and the current devices does not satisfy these needs. Also, experimentally, single qubit gates, they are efficient to perform, they present almost no noise, but the two-qubit gates, they are extremely noisy, and this is due to the cross-resonant effect, mainly. Several works have been carried out in the last years, and the fidelity of the two-qubit gates have been increasing, but still it is so difficult to have long coherent times and a small amount of noise to perform long-depth quantum algorithms, quantum circuits that in the end are quantum algorithms. So the crosstalk is an experimental limitation that prevents us to use the current device that we have in the field of, and keep developing the field of quantum computing. So the idea is, what if instead of seeing the crosstalk as a problem, we saw it as a resource, since it is something that is going to happen either way between the qubits that forms the quantum processor. So instead of look at them as a problem, let's use them as our friend. And this is the main idea behind the digital analog paradigm. These paradigms, is the building blocks of this paradigm are digital pulses that are single qubit gates, the same as in the fully digital case, and analog blocks that are performed by the time evolution of the interaction Hamiltonian inherent to the quantum processor. This means the natural Hamiltonian that arises between the qubits. With this, we do the same thing as we do in the digital paradigm. We change the state of the qubit and create entanglement and superposition in the whole system. So digital analog combines both the flexibility of the digital paradigm and the robustness of the analog simulation. Let me try to convince you by presenting you a tiny example of how this is done. We are going to simulate an inhomogeneous all-to-all two-body Ising Hamiltonian. The resources we are going to have are the interaction Hamiltonian, which is the homogeneous Ising Hamiltonian, that one, and single qubit gates, which are going to be X rotations, just that. The goal, we want to simulate the all-to-all two-body Ising Hamiltonian with arbitrary couplings, that one. For doing these calculations, we are going to use a 3-qubit quantum processor connected in the way that I am showing you, so a simple triangle. And the coupling constant is going to be the same for all of the qubits, since the interaction Hamiltonian is the homogeneous one. The interaction Hamiltonian for 3 qubits is that one, so I take this formula and change the n by 3, simple. And what we are going to do is perform single qubit rotations on the different qubits of the system, and then let the system interact during a certain amount of time. We can do this. It's interacting still? Okay. Okay. Every time we perform the single qubit rotation, we let the system interact and then perform the inverse of the rotation we have performed. So we go back to where we were. And since the rotations are going to be x gates and the bodies we have in the Hamiltonian are z gates, whenever we do this, we will see a minus or a change of sign in the Hamiltonian that represent our unitary operation. Okay, we can apply the single qubit gates different ways. We can apply it in the first and the second qubit, the second and the third one, or the first one and the third one. The operation is the same. Single qubit gate, I go up in the Hamiltonian part of the exponential. Single qubit gate applied on the different body, and I end up with this T1, which is the time that I am letting the Hamiltonian evolution be applied. This T1 and this different sign before the two-body terms. If I apply it in the first one and the third qubit, I get the same, but the signs are different. And if I apply it in the other way, it's the same. Let me put everything together. And in the end, this whole operation is represented by this unitary evolution of time T1 plus T2 plus T3. And what I have, it's something so similar to this inhomogeneous Ising Hamiltonian, where these terms that I have before the two-body terms can relate to this coupling constant that I wanted to get. So in the end, the whole problem reduced to find a map between these terms and the other one. So it's easy peasy, lemon squeezy. Okay. Yes. Voy para atrás, sí. Ah, the other one, sí.
Yes, so you're assuming you can control when the analog blocks are switched on and off.
Yes.
Something that you can do it.
Yes, but you can do it easily, but that takes some noise and some errors that I'm going to tell you about right now. But yes, this is assuming that you can turn on the interaction and turn it off again.
This is true in the devices, right? Do you have that degree of control? Or
If I have a?
That degree of control, so in the devices you are...
Experimentally?
Yes, in the devices you are doing.
In my imaginary devices that I use for the simulation, yes. In the experimental ones, I don't think we have that amount of control. Because I don't know actually how the experimental devices, I haven't worked with an experimental device yet. But I don't know. I assume that it's not that easy for the experimental device. I don't know. The idea is that they should be, but I don't know. Mikel? Sí, pero experimentalmente, is it possible to do this now? To put the interaction on all of the qubits at the same time? Turning on and off? Yes, okay, vale. I'm going to keep talking.
You use it to intermediate in order to reach the bank.
Yes.
The bank is the one that you don't have, like
But I have the same question in the bank one. Experimentally, is it possible for real to put all of the qubits in communication? Bueno, okay, I am going to keep on with the talk. Maybe I understood the question wrong. Let me guide you through. Vale, what I have told you about is there are two approaches of the digital analog paradigm. The one that I have shown you is the one that is called stepwise, and this is done by switching on and off the interaction between the digital blocks. So first we apply the digital pulse, then let the system interact during a certain time, turn the interaction off, apply the single qubit gate, and then again turn the interaction on, and so on and so forth until the very end of the process. But this face a lot of errors whenever we try to turn it on, try the analog block to stabilize and then turn it off. In the end, it takes a lot of error in the simulation or in the performance. So there is this other approach that is much better, which is the one that Mikel was telling now. And the idea behind this is to first turn the interaction on, let the system interact, and the single qubit gates are performed on top of this interaction. This way, we are not performing the exact equivalent operation that we might have done by applying the stepwise paradigm or the fully digital one, so we are introducing some inherent error, but this error scales up much better than both the stepwise and the digital paradigm. And this is because the time that the single qubit gates takes to be performed is much smaller than the interaction time. I think 2 orders of magnitude, I could say. So this, yeah. Okay, the system is interacting and the single qubit gate. Okay, so to show you how does the, oh no, how this error scales up with the number of qubits, I think the good idea is to show you the result that we have when we try to implement the quantum Fourier transform. We did the simulation and performed the quantum Fourier transform. This is the circuit for the 3-qubit case, but we did it for 3, 5, 3, 5, and 6 qubits. And we took into account the experimental errors that we might face. So these are the errors that we might have in the application of every single qubit gates, both in the digital and the digital analog. The experimental errors in the application of the 2-qubit gates. This only applies to the digital one. The same for the analog blocks that apply only to the analog blocks, so switching on and off and the unstable sign and whatever. And then for both cases, we took into account measurement errors, bit flip, the coherence, and the thermal relaxation. And we performed this quantum Fourier transform. We apply it to a family of states, which is this one. W and GHZ are just family of quantum states that makes no difference, so I haven't put them here, but this is just a family of states. The figure of merit is this fidelity. And well, here, this is not time. Sometimes I get this question. This is not time. This is the different values of the beta angle of the family of states. So this figure has a lot of lines, so let me guide you through it. Let's take the 6-qubit case, which is the green line here. The digital version of the application has this kind of fidelity. So it's not the best one, but it's much better than the stepwise application of the quantum Fourier transform. The stepwise has a really bad fidelity. But the good thing is that the bank DAQC is the one that has the best fidelity. The fidelity is always above the digital case. And this also repeats for the 5-qubit case and the 3-qubit case. So this, are you suspecting? Ah, okay.
So the reason of that is because you are implementing the gates or?
No. In the end, you are getting rid of a lot of 2-qubit gates. In the 6-qubit case, you have a large amount of 2-qubit gates, which are the noisiest one. So you are getting rid of all that 2-qubit gates, and you are only having single qubit gates, which are free and analog interaction. So whenever you go up in the number of qubits or in the depth of the circuit, the bank digital analog looks like the best option for you.
So you are removing the cost.
Yeah. Yeah. The only thing you need is a digital analog quantum computer, but apart from that, okay, so why did we focus in the beginning of times on the quantum Fourier transform? Because it is a building block of a lot of quantum algorithms and quantum subroutines, but mainly it's a building block of the HHL algorithm, which is an algorithm that was proposed in 2009 by these guys, Harrow, Hasidim, and Lloyd, to solve linear system of equations and, in the end, matrix inversion problems. The running time of this algorithm is polynomial of the log of n, which is the dimension of the Hermitian matrix A. So this means that it's exponentially faster than any classical algorithm. I don't know how I'm going to with the time. This algorithm, it's kind of hard to fully see all of the part and how does it work. My intention was to try to guide you through it and show you and explain it, but I don't know. Vale. Maybe I need some faith from you, but I'm going to try. First, the algorithm in a nutshell And then we can go step by step. First, it represents the vector B. I don't see the arrow, but it's a vector. Represent the vector B as a quantum state. Then use quantum phase estimation to decompose that state B into the eigenbasis of the matrix problem A and find the corresponding eigenvalues of the A matrix. Once we have done this, the state of the system is more or less this one, if everything has been done properly, like experimentally properly. This would be this alpha U sub j, this would be B, the B state, and this lambda j would be the eigenvalues of the matrix A. So these are binary codified into the family of states. Then, this is the magical part. This is the magical part. The algorithm performs a linear map that takes this codification of the eigenvalue, I don't know if I'm in the middle, of the eigenvalue to, that's this map. The codification of the eigenvalue goes into the coefficient of another state, and in fact it doesn't go straightforwardly. Joder, macho. This is so hard. Sorry. Takes the binary estimation of the eigenvalue, takes out from the state and goes as a coefficient in the form of the inverse of that eigenvalue. Okay, I will show you later. This is horrible, sorry. And then finally, it performs an inverse quantum phase estimation to uncompute all of these states from the registers. So we go back to a zero state in the register, and in the end, by measuring the system, we are in this state, which is proportional to up to a normalization constant, is this alpha j u sub j, which comes from the B, this inverse of the eigenvalue that came from the magical map, and in the end, this is the solution of our linear system of equation. I'm really sorry. Okay, let's try it again. We start with well, let me tell you that the qubits in the algorithm are grouped in 3 groups. We need 1 qubit for the ancilla part, which is the ancilla qubit, 1 qubit, only 1. Then we have the register qubits. We need at least log 2 of the dimension of the matrix problem. The more we have, the more precision that we have whenever we compute the eigenvalues of the matrix A. But at least we need log 2. And the memory qubits, since we are going to represent the B vector, we need log 2 of the dimension of the B.
It is exactly the same as the dimension of A.
Yes, but with a B. But yes. So let's assume that our initial state is this one. Everything is in the zero state, except from this memory qubit. Why is this? Maybe you can get this information either by uploading this information, which is a problem itself, or maybe this HHL is a subroutine of some bigger problem, so this B vector already came from before. So we are going to assume that we already have it. We get rid of both problems. Next, we perform this quantum phase estimation. After performing this evaluation, ¿se ha puesto blanco? We have this state. So we have done nothing to the ancilla, so we are still in the zero state. The memory qubit is is decomposed in terms of the eigenvalues and eigenvectors of the matrix A. So this is alpha u sub j, u sub j. This is the B vector here. And this is what we get after we perform the quantum phase estimation. The quantum phase estimation itself, it's a whole other world. So here is the phase that I am asking you to have. After this, you get this state, this beta sub kj and the state k, and this coefficient is this one. This lambda j is the eigenvalues of the matrix A. And if we relabel this k over 2 to the end as lambda k, which is the binary codification of the eigenvalue lambda by these definitions here, we can say that after performing this quantum phase estimation, we are in this state. 0 in the ancilla, the B vector here, and there's this kind of coefficient with the lambda k in the registers. So here we have a superposition of the estimated eigenvalues of the matrix A. This is this connect with what I told you about the more qubits I have in the register part, the more precision I have here, because I have much more precision in this decomposition. Okay, magical part, ancilla quantum encoding. The map that we wanted to do, that this was so difficult for me to say, is that we start here, the 0 ancilla and the lambda k, the estimated eigenvalues in the register, and by this magic quantum computing one, we get into this state. So the lambda, the register is in the same state, but we have managed to take the binary information here, translate it into the decimal information, and actually put it as the inverse of that number. And this C is just a constant that might be this one, or it is related to the sparsity of the A matrix, which I didn't mention because my head is going to explode. Okay, is it more clear now than before, this magical map? Okay, it is not. Do you want me to tell you more about it? I mean, the nice part is not this one, it's the rest. Vale, I'm going to keep going. I am sorry, guys, I am sorry. Vale. Okay, so this magical map. We have the magical map. So actually, we have, the system is not only this lambda k estimation of the eigenvalue, it has this B vector too. So the final, vale. So this is what we have after the map. And if everything went correctly, this mapping part was efficiently performed. Well, what actually is called perfectly estimated. Then the beta vector that appeared in the quantum phase estimation part is just this one, maybe this is useful. This beta coefficient, if this lambda k is more or less the same that I wanted to get, so the eigenvalue of the A matrix, this is going to be a 0. So if everything was perfectly estimated, this beta coefficient translates to this one. So the final state is just magical map, the B vector, and the lambda j. So we don't have any estimation. We have the real eigenvalue of the A matrix codified in the register. And also the estimated one as a coefficient, the inverse of the estimated one as a coefficient of the ancilla qubit, related to being in the excited state. Sí, sí, por favor.
That definition of the constant C?
That definition of the constant C is not proposed by the original authors, but by several iterations of this algorithm. It makes me think that it's A to the A minus 1.
Yeah, that's the solution to the system you are trying to solve.
Yeah, so I assume that it's of the order of that one. In the end, what I have seen, but I don't have the demonstration, so I didn't want to put this, is that C can buy more or less 1, depending of the sparsity of the matrix that you have. Maybe I can tell you more about it. That if you already knew this information, then you don't have any problem. So something is around here, but maybe later I can tell you more about it. Vale. Okay, so the next step is simple, just perform the inverse quantum phase estimation just to reset all the registers to the 0 state. So the final state that I have is the B vector here, and the magical mapping that I had with this constant that it can be similar as 1. Well, and that state in the ancilla qubit. So now, to end the algorithm itself, one just have to measure both the ancilla and the memory qubit, and the information it takes is it's a conditional measurement. So we measure the memory qubits conditioning on having the excited state in the ancilla qubit. So what we have, it's actually the solution. We have this. This is the state of the memory qubit. This is the coefficient of the ancilla qubit whenever it's in the excited state. And up to a normalization, it's the solution of our system. If everything went properly. ¿Qué te pasa, Miquel?
You are measuring the memory.
Yes?
You cannot obtain X.
You can?
You are measuring X, so you cannot obtain X.
You say here.
You are measuring the memory.
Yes, here you okay, maybe this is wrong from my side. I don't mean that you have the X solution here in B. The X is the combination of measuring the ancilla qubit, both things conditioned on C in 1.
So the solution is not in the memory, it's in the register.
No, the register are back to 0.
Then you can measure in X. So you can measure in the ancilla, and then the X will be the solution. X vector will be in the memory, but you don't have to measure. If you measure in the X, you obtain the mean value of X with something.
But if I measure both conditioned, I don't get the mean value, I get the whole solution. No? Well, a ver, maybe I'm not understanding your question. Eh?
So if you are measuring this, you obtain something that is a vector in the register.
Mm-hmm.
It's the only thing that it keeps.
No. In the register, you are not touching anything. The register are reset to 0, and you are not measuring them, actually.
Yes, so therefore, it's the only thing that remains as a quantum system, as a quantum state.
Why is that? I don't
Because the
understand.
other ones are measured. If they are measured, they are measured.
Yes, but I mean, you have to measure to know the solution to your problem. If not, okay, I think I understand you. If you are going to keep doing operations after this one, so you don't want to measure and you want to work with this solution of the problem, is it enough to measure the ancilla qubit? Is that what you're saying?
Yes, so if you want to obtain a state in the memory qubit, if it's a state you want to obtain there, you cannot measure that, because if you measure there, you are destroying it.
Vale, okay. Okay, then we
But
take
actually,
this
you
one.
never want to obtain X. You want to obtain the mean value.
The mean value of X, that is true.
Because this is not efficient. You need
That
to
is
make
true.
a Futomura.
Yeah, I don't know. I thought that maybe for seeing what this HHL does, I thought it was better to show it that way. Otherwise, it was like. But yeah, you're right. ¿Qué ha pasado? Okay, so after this whole computation and algorithms and stuff, this magical map that I told you about, I insist a lot in this part, because in the original article, of course, they don't propose how to do this. They don't propose, and they doesn't send you any guide or no. They say a linear map that can be magically done. So, in other words, the way that they have faced these things is either to reduce the problem, so have a tiny problem where you can also get the solution classically and then try to see if the quantum version went fine. And in fact, what they do is they take these little problems and they manage to get this ancilla quantum encoding by hand, like which gates do I need to apply it. So that doesn't serve us. The other thing that they have done in other works, but mainly it's all taken in this paper, is to do it in a hybrid way. So this ancilla quantum encoding is performed by a classical computer. They measure what happened after the phase estimation process, compute the information that they had, and then plug it in on the circuit and keep doing all of the things. This is also nice, but you need a classical computer to do that. And the thing that we have worked for the last years is on a way to do this quantum encoding that is systematical for any linear system of equations, so you don't have to have a small problem, or you don't have to know your solution, because otherwise you don't have a problem, and you don't need a classical computer. So we found out this kind of operations that is big. I see that. I know that it is so hard to do in a digital quantum computer. I know. But we have seen that we can remain only the terms with one and two body interactions. We can get rid of the rest of the conditioned operations. That takes a lot of work for the quantum computer. And even though we are not getting the exact solutions, the error that this takes is first controllable because we know more or less what kind of error we can face. It is not representative to the final codification of the circuit, and it allows us to have a fully quantum implementation of the HHL. So in the end, you only need 2-qubit gate and two body terms. This is good. Why? Because it allows us to perform this HHL in these digital in the next devices. These devices, but also because we know how to simulate digital analogly two-body Ising Hamiltonians. We know how to do it, and we know the error that it takes, and it's not a big error. So this is good because this is good for both paradigms, the digital and the digital analog one. Please.
Would you have still quantum advantage with that implementation? I mean, in the happy world where everything don't exist?
I have doubts, actually, la verdad. Because the runtime was with log n, but it shouldn't, a ver. I have doubt, but I think that it shouldn't complicate the things too much. I mean, experimentally, it's so difficult to achieve this whole part. But in the magical world of mathematics, I think the runtime error would be the same. I think so. This doesn't affect actually to the complex.
Depends to which quantum advantage because you have two things here. One is the size of the matrix. The original paper is claiming a quantum advantage in the size of the matrix, but it's in the size of the memory. But this one, the number of terms depends on NR, which is the precision of the eigenvalue. Of course, the precision of the eigenvalue has to grow. If you want to distinguish between different eigenvalues, you need to grow with the size of the matrix. But they are independent parameters in general, so it does not affect if NR is small. It does not affect the size of the matrix. You can still have very large matrix.
Yeah, I was thinking all the time because if that kind of implementation you found takes a lot of gates.
It takes an exponential number, but the exponential is NR, which is not the size of the matrix.
Okay.
So if but they are independent, you can choose a small NR and still grow in the size of the matrix. Okay. Which is the limit. So this is the point. You can still have a quantum advantage for the size of the matrix.
So I think that you will stay in the polynomial time of the poly n, the dimension of the matrix. And I think this is all. Yes. So this is the work that we have been developing, and this is the thing that we are finishing by writing the paper and stuff. We think that it is a powerful and a strong result in both ways, that complete the whole HHL implementation systematically and allows for some experimental implementations. Maybe on tiny systems first, but I don't know. This is it. That's it. I have some conclusions about the digital analog, but I think that it's already more or less taken care. And thank you all for your attention. Questions?
I have one.
Yes, sure.
In the first place, you mentioned the noise in the 2-2 gate,
Mm-hmm.
and you mentioned the crosstalk.
Yeah.
Can be as a resource and in the digital analog. So I'm not quite getting why this crosstalk can be a kind of a resource in the digital.
Can you repeat? So what are you not understanding? The crosstalk with the? I didn't understand.
I mean, the crosstalk is kind of a noise in the two case.
Yeah.
And why you mentioned this is could be
A resource.
in
It's more like the whole idea behind the crosstalk is something that happens between the two qubits that they are interacting, even if it's a little bit, even if you try to isolate them in current devices, it's so difficult to do this, so there is some crosstalk among them. So since this interaction is going to happen already, why instead of trying to isolate these two qubits, let's put them all together and let them crosstalk, so this crosstalk wouldn't be this crosstalk, would be the interaction of the Hamiltonian.
So, yes, if it's isolated, and then when we consider this noise, yes, maybe it's not perfect, but in the circuit, like put it together, like it can be a resource, like for the.
Yeah. ¿Eh? Ay, Dios mío. Venga.
If you go to in the description to HHL in the very beginning, you are using, well, actually it's the same question but twice.
Esta.
Yeah. Here you are assuming that you can decompose B as the sum of alpha uj, where uj are the eigenvectors of the matrix A.
Yeah.
And additionally, if you go to the next slide,
Más?
yeah, here.
Okay.
And here, the control rotations depends on lambda k, which are the eigenvalues of A.
The control rotations, which control rotations? This one?
Of the quantum free estimation of AQA.
Esta. This one.
Yes, well, the result of the AQA, after.
So this one.
In the equations, yes, exactly.
Okay.
This is square root of 1 minus c squared divided by lambda k squared.
Yeah.
So this depends. The rotation depends on the eigenvalues of A, lambda k and the eigenvalues of AQ. But if you already know the eigenvalues and eigenvectors of the matrix A, why do you need to run everything?
Because you don't know the eigenvalues of the matrix A. The phase estimation algorithm encode the eigenvalues of the A matrix in the register, but you don't know them. In advance, you don't know them. And in the middle, you don't know them either.
But you are using them.
Because they are here. Sí, Rubén. Ah.
It's another question.
Vale, pensaba que era related. I am using them, but I am not measuring them. I am not measuring them. I don't understand where are you going.
I mean, you are just using your protocol, you are using
yes.
You can decompose it, but if you already know this decomposition.
I don't mean that you can decompose it as you know how to do it, but if the information, Mikel, you don't know how to decompose them because otherwise you don't have any problem, but you can assume that it can be decomposed in the eigenbasis of A. No?
I know the answer, but I mean, it's just.
Mikel? Okay, maybe we can talk about this later. You are not decomposing the B vector. You are plugging the B vector in the phase estimation, and when you perform the phase estimation subroutine, if the input state is already in the eigenbasis of the A matrix problem, it performs all of these operations. But you don't have to know. I don't see where are you going, Mikel.
No, I don't know where you are going to. So what you are using is that you can decompose it, but you don't need to know this decomposition because you are never using this at the end of the protocol.
Of course, but
this is just in the intermediate step, but not.
But I don't need to know this decomposition in the implementation of the algorithm, but I need to know that it can be done in order to. I need to know that it can be done in order to show what is behind the whole algorithm, not the implementation.
And you only use it in the intermediate step, but not at the end. At the end of the algorithm, you don't measure So it's not necessary. You only need to know that it's possible, not which is the actual
Okay.
decomposition itself.
Okay.
And the same with the rotation. You know that this control in the composition of multi-control rotation that you are using, you are not using anywhere that the eigenvalues.
No.
However, at the end of the day, it's equivalent to have the control, the constant c divided by lambda k and so on, all these rotations. It's equivalent that you are not using, you are not using information about lambda k.
No.
This is something that you have to stress out. It's important
Okay.
because if you already know the eigenvalue, if you tell it in this way, it seems that you already know the eigenvalues and the eigenvectors.
Okay, I see, I understand.
All you do is useless.
Vale, I see now what you were telling. I mean, I have it already in my head, but maybe I should have stressed it out.
And just a small comment, it's not true that the register activity is the log 2 of the mentioned effect. This is independent. This was the answer that I gave to Carlos. It's just the precision for the NR is independent from the size of the metric.
But I mean, what I want to say with this, maybe it's not clear. I mean, here in this part, I am letting know how many qubits do I need. For the register, at least I need this, but I can use more. But that's the only implication.
Why at least you need this one?
Why at least I need this one? To be able to encode all of the eigenvalues of the A matrix.
No, but you can have several of them that are equal. You cannot distinguish.
Bueno, okay, vale, I can have less, but the precision is going to be ridiculous.
That was my question. Have you considered the error introduced by the quantum phase estimation being perfect? Because quantum phase estimation is not perfect if the values are not exactly a multiple of.
We have taken that into account by knowing that at least it would be good to have log 2 of the dimension of the A matrix, because otherwise the precision is going to decay fastly. And by stressing out that the more we have, the more precision we have, but we haven't studied like how does the error scales with the precision of the phase estimation. Maybe it's interesting to do that. Guiño, guiño.
But there is another error because they are assuming that you are uploading A exactly with infinite precision. A cannot be uploaded. A and B cannot be uploaded. You do it with
Yeah,
precision.
that's another problem.
And this is carrying all the process, all the other. Because keep in mind that when you are introducing the information, you are not introducing the information bit by bit. So you don't control this. You are introducing it as a phase of a Hamiltonian or phase of the vector. And this one is not, it's an error that you can estimate that you cannot control completely.
Okay. Toma nota.
And this also justifies our claim that you can introduce an error in the ancillary quantum encoding and reduce the number of things.
Yeah, there is also a lack of precision inherent to the process. But we cannot control everything. You have more questions?
I have one.
Please.
In the slide that you present the digital analog scheme, you say that you only need one and two body iterations. No, for the HHL.
Ah, the HHL, okay. So, here.
Yeah, you say that you only need one body terms and two body terms. I don't know exactly what you mean, two controls?
No, okay, yes, this wasn't clear. Two body terms, meaning these ones as body terms. I wanted to do this, to talk about this like in a short version, so I didn't came into details, but all these multi-control operations are represented by different projectors, and in the end a whole Hamiltonian, and the terms that participate in each part of the Hamiltonian. I have one term when I have a 1 in the codification of the eigenvalue. So here it's set in the 4th qubit, set in the 3rd qubit. So this is a 2-body term, this is another 2-body term, this is a 3-body, no. Yeah, it was like a... The intuition behind the whole idea. When we compute the Hamiltonian of different amount of qubits, we saw with the eye that the I mean, this I tell you, but maybe no te preocupes. How does the coefficient grow? How the coefficient behave for each term of the Hamiltonian, and we saw that there was a significant difference between the two body terms and the rest, the one and two body terms, and the rest of the part of the Hamiltonian, significantly different. Hopefully, the next talk I can show it, like just the HHL and this kind of details, because it's not.
It's a numerical evidence.
No, I mean, it's a scaling. So for one and two body terms, the coefficient that depends on NR, on the precision. While for three or more, it decreases exponentially with NR. So if the precision is large enough, then these terms are exponentially suppressed, while the other ones are not, or more or less not.
Yes, please. No, hombre, claro, lo que quieras.
No, so my question is related with this question, right? Because so when you want to, okay, typically, I mean, there are some kind of coherent interactions that you can use it, right? And there are some noises around. It seems that in your case, this is because the process of other qubits, right? And that qubits, okay, you say that it's a kind of crosstalk, right? And typically it's considered a kind of error because it's tiny, right? But it's always there, so you can, I mean, it's not good to accumulate, right? However, you said that, all right, I can, instead of considering it as an error, I will use it as a kind of interaction, right? But correct me if I'm wrong.
Okay.
But if it is tiny, right, all right, that kind of interaction that you consider as an error, and you can consider as an error because it's tiny. But then now you want to include it, but continues being tiny.
Okay, I
That
see.
means that I mean, if you want to include it coherently in your design, right, the time that you could need is long, right, for letting this kind of term, let's say, appear in the dynamics, right?
Yeah.
Is that true or not? Or is that true first? Is that true or not?
Yeah,
If this is true, is that a problem or not?
Okay, I see. It's true that the crosstalk it's considered as a tiny error in these next devices whenever you want to perform digital quantum computing paradigm. But if we go to the digital analog part, you don't want to use a computer which is developed for digital quantum computing, which is perfectly isolated and the crosstalk is tiny enough. You want to, it's just only the idea that they are going to interact. So instead of trying to make it as tiny as possible, make it as bigger as possible so you can use it as an analog interaction.
All right, so you're assuming that in some way, I mean, you have the elements, this coupled with this, coupled with that, I mean, you can more or less, I mean, all the couplings are of the same, yeah, magnitude. So that's something that you can control, essentially, that's what you are doing.
The interaction of the qubits,
so
or at least that you know, and you know it's.
All right, so in the typical construction, this is the coherent interaction, and this is the noise, right? And the idea is that you want to remove the presence of this. All right.
Yeah. Okay. Julián.
In the middle, you make some simulation to simulate the quantum the quantum Fourier transform that you make for 3, 5, and 6. Yeah. What is the structure of the device that you are using? Because you are assuming the 3 is a trial model, but when you are 6, all the qubits are connected, or are only there's?
We are assuming that the processor has all-to-all connectivity. Of course, experimentally, this is kind of hard to get, but that's no problem because it is also, the reference is actually here. Even if you have only nearest neighbor architecture on your device, it is possible still to simulate an all-to-all Hamiltonian. So you can think about it like as different steps. With the nearest neighbor architecture that you have, you can, I don't know if the simulate is the exact word, but let me use it. Simulate an all-to-all structure, and then with that you can simulate the Ising Hamiltonian that I showed you. It's actually this work by Asier Galicia, here, then has connectivity.
Yeah, it's this one that have the star.
Yeah. So we assumed that because it was easier, but also, to be fair, we assume the same one for the digital case, which is also as impossible. So we thought it would be easier. Please, more.
Okay.
Paper.
I have
Oh,
one
well,
question. In the beginning, you introduced this bank approach.
Yeah.
Bank approach.
Bank, yeah, bank, this one.
And well, at first you turn off the interaction, but is it only in the theory where you turn it off, or also in practice?
The idea is
Because how to turn the interaction off?
in practice is to put all of the qubits to interact among each other and then being able to stop that interaction. Experimentally, it's hard, and in fact, you can see that in the simulations, the stepwise, the fidelity decays fastly with the number of qubits. So I understand that your question, like, but how can you do it experimentally? This is like more like a middle step to get to the bank, which is actually what we are interested. So the bank digital analog, which you can. The interaction is going to be present, and it's going to be present during the whole process. So I wouldn't be worried about this part. This is only as a middle step. Hombre.
So you are planning to implement this in some quantum computer in the cloud, or what is one? So you are developing this specifically for some?
For some specific digital analog computer, no, because I don't know how to do that. I mean, I don't know how to do that. Sorry, I don't know any digital analog computer. Maybe with some experimental groups, it is possible, depending on the hardware that they have and how do they work with them. If they are extremely no, but so focused into reducing this crosstalk and isolating well the quantum, the qubits, sorry, this would be hard to implement. So maybe going more to the other side. But you can also implement. Bueno, no, no, a ver si la voy a liar. Up until this point, yes, but trying to be as realistic as possible, so we can actually implement it in different devices. Okay.
Yeah. In the normal digital analog, not the bank.
The stepwise. The stepwise.
Yes. What's the difference between that and normal digital computing? Because they also have to suddenly tune the interaction between. They do the two qubit gates that way.
Yeah.
So what's the difference?
The difference is that you are not thinking about which qubits to put together to interact, but you take them all and interact at the same time. During this period of time. This different period of times, also that's a different. The 2 qubit gates take an amount of time, and it takes that amount of time. But the analog blocks take different amount of time depending on the simulation you want to perform.
Yeah, related to Jorge's question. Is there any physical platform close to the level of accuracy or you need to implement this? Or you see it like fast from now?
Carlos has an idea for that. Carlos has an idea for that.
I mean, that kind of interaction is what you have in MPs. So, MPs are that. That's it.
The interaction has very fast single qubit gates.
Okay, then that sounds a lot like.
An array of cold, let's say 4 Kelvin MPs would be suited, I guess.
Hombre, but sounds. This one. That is perfect because this one we don't like it. So no, that would be really interesting. Maybe you can tell me more about that later. But also, I don't know. Maybe Mikel, if I would say, but please help me if I am lying. In the end, NMR is so similar to this, so maybe that kind of platform can be used to do this. If not, I can take the door and leave.
It was the way that it was proposed in the early 2000 to do computation with NMR. With NMR. But the problem is that the coherence is so fast that actually it was proven there is a PRL in which they proved that for more than 7 qubits, this is not anymore quantum.
Okay.
This figure is simulated classically.
So that quantum Fourier transform, we could have performed it in an NMR.
Instead of having a vacuum, like here in the quantum circuit, you have a thermal state. And the thermal is so thermal that everything, any quantum coherence is fast load.
Okay.
To have these kind of interactions also in superconducting circuits and in trap ions. The point of trap ions is to have all-to-all direct interaction, but the point of superconducting circuits is that you have the scalability somehow. You can use this trap ions. I mean, answering the question, your questions, the other day, you wrote the paper by
True.
With 65 qubits of quantum linear network, 65 qubits is in digital analog, and there are other experiments in China about digital analog. But it works at least in superconducting circuits, it's always proven. But answering your question before, there is something that Anna has not explained in the very beginning, which is the difference between a digital gate and an analog block. This is key in order to understand the difference. And the difference between these stepwise is that you have a continuum time as a parameter. In digital, you have gates, and the gates are for a given time. So it's P over 4 or whatever. And this is the difference between a digital gate and an analog block. An analog block you also use as a resource the time, the in front of the fountain, time of evolution. And so this block, even though it looks very digital, it's you can play with the time. You have different widths.
Okay.
Yeah, okay. Any other questions? No?